All right, we've got a small group here today. I don't know if that picked up on camera. Okay, so the first order of business. Last class I handed out your take-home exam, right? And I decided I'm going to change problem number 3. I've already changed it online, but I'm going to hand you a whole new, fresh copy of number 3. And the reason why I'm changing it is because originally when I made that problem, the instructions were to set up the integral but not evaluate it. And it's practically impossible to evaluate by hand. So I made a problem that you will be able to evaluate by hand. Fair enough there. Here, you take a couple of these extras. Yeah. Okay, that's the only thing that's changed. Problem number 3. All right. Originally, I believe it was a sphere, so it changed. Everyone got that? Number 3 is changed. Extra.
Yeah, you changed one problem.
All right, let's get started. Yeah, I changed it online also today. I didn't send an email, but the files online have been changed. All right, so today we have a lot of work to do. We're a little behind right now. And so I'm not going to try and go too fast, but I do want to kind of pick up the pace. We're going to do double integrals in polar coordinates today, chapter 12, section 3. I was at that number 8. Yeah, anyone else who did number 8, you can turn that in. I have not had a chance to grade your mini exams yet. I'm still working on those, so. All right, so we're going to do double integrals in polar coordinates. So right now we have talked about double integrals over 3 types of different shapes when it comes to talking about the domain. We first started with the double integral over a rectangle. Then we had this type 1 region where our x's were bound between 2 constants and our y's were bound between 2 functions of x. Then we did a double integral type 2 region, which was our y's were bounded between 2 constants and our x's were bounded between 2 functions of y, right? So that's what we have done. And now what we are going to do is look at some more interesting regions that we can't easily describe using our Cartesian coordinate system. So first, let's remember that if somebody gives us a point in 2-dimensional space, it must have an x and a y coordinate, right? And the way that Cartesian coordinate system works is that we start with a place that we call the origin. From the origin, we construct 2 axes, the x and the y axes. These 2 axes are orthogonal to each other, perpendicular, right? And then to describe a point living in a Cartesian 2-dimensional space, the x and y values tell us how far we would travel in the direction of the x-axis and then the y-axis respectively. So if this was 2, 3, this would mean go out this way 2 and up 3, right? That's Cartesian coordinates. And when you're in 3-dimensional space, it's x, y, z, right? And you have 3 axes in 3-dimensional space as opposed to 2. So in order for me to describe a point in 2-dimensional space using Cartesian, I need 2 things, don't I? X and y. But there's another way to get to that same point that eliminates the need for the x and the y axes. And that is, if I want to get to this point, I can instead point out this direction, still in the direction of the x-axis, and tell you how much to turn by. So I tell you, turn by this angle, and you rotate, and then I say walk out a certain distance, which would be r, and that would take you to the same point x, y, wouldn't it? So there's 2 different ways we could get to that point. Cartesian x, y, or this other thing, which we call polar coordinates, which gives you an angle and a distance to walk. So we know from pre-cal, that there is a relationship that we can establish between the x and y coordinates and the angle and the radius or the hypotenuse of this right triangle, right? So cosine of theta would be x over r, sine of theta would be y over r, and if we mess with those equations, we come up with that x is r cosine theta and y is r sine theta, right? Remember that from pre-cal? So this polar coordinate system, in order to define a point, you still need two things, right? What are they? Theta and r, right? You give me theta and r, I'll tell you where I'm going to be. You give me x and y, I'll tell you where I'm going to be. So both Cartesian and polar require two inputs, but it's just those inputs have different meaning, right? Questions? Change the radius, right? Change the angle. I can get to any point I want, right? Like that. All right. I think this is a little too big. Let me go smaller here. Just want to make sure I'm recording. See a red dot up there? Yeah. Okay. All right. As we continue here, let's set up some relationships that we have. I can barely fit that on there. Let me make this a little smaller so this all fits. There we go. That didn't work. There. Okay, so the relationships we have from the right triangle, Pythagorean equation, right? X squared plus y squared is r squared. So that's a relationship between x, y, and r. What we're trying to do is we're trying to figure out a way to go from Cartesian coordinates to polar, or from polar back to Cartesian. So these are the relationships that we're going to be using here. This equation, of course, the relationship between x, r, and theta is this from pre-cal, between y, r, and theta from pre-cal, and then there's one more from pre-cal that if you want to know what the angle is, you can take arctangent of the y coordinate over the x coordinate. And just remember on the arctangent, you have a domain restriction. Your domain restriction for arctan is between negative pi over 2 and pi over 2. So those are the main relationships between Cartesian and polar coordinates. So remember that when we were talking about a rectangle in Cartesian coordinates, what we were saying was that we had this interval AB crossed, even though we said it wasn't cross product, crossed with the interval CD, that this was the restrictions on x's, this was the restriction on y's, and we drew this rectangle, right? That's a rectangle in Cartesian coordinates because it says our x is bounded between two constants, our y is bounded between two constants. But what would a rectangular polar region look like? So instead of your x and y being stuck between two constants, what if your theta was stuck between two constants? Because, right, polar, you need theta and r, right? So what if your angle's stuck between two constants? We like to use alpha and beta as our constants, a, b, right? But in Greek letters, alpha, beta. And then our r is stuck between two constants. We use the regular script a and b, ab. So what would that look like? Circle? Let's see. Here's what it would be. So let me change first of all the angle. Okay, the alpha is the small angle, okay, the first angle. So I'm going to go from here to beta, which would be that angle. So that's where I start. I want to swing through that angle and stop at this angle, right? And then my radii, because there's two of them, my smallest radius is how far I walk out, right? I can adjust that. And then my outer radius, I can adjust this. Did y'all see that object? This is a rectangular region in polar coordinates. It doesn't look like a rectangle, right? Not a traditional rectangle. All right, with me? So remember from double integrals, when we first started, we were integrating and we were doing Cartesian coordinates, we weren't even talking about polar yet, but the way we set it up was we said that this little differential dA, right, represented this infinitesimal little area, which we got by putting dx and dy and multiplying, right, because area is, you know, width times height or length times width, however you want to say that, right? And this right here, this little dA, is a rectangle in Cartesian, right? So if we do a double integral in polar coordinates, our dA is going to have to be a rectangle in polar coordinates, which we just saw what that looked like, right? So take a look at this. This is kind of a complicated picture, all right? If we want to do a double integral of some function of r and theta instead of x and y over some region r with respect to area, then we need to know what the area of that red piece is. It's not as simple as the area of a rectangle back in Cartesian, right? It's not just length times width. Yes? Okay, so let's try and figure out what this would be. There's something you have to remember here from pre-cal again, excuse me, that if, how many of you remember this formula? What's that? Arc length, yes. So you remember that formula? S is equal to r theta. This is if you start here and you swing through some angle theta, then this arc right here, S, and if this side was r, then S would be equal to r times this angle. Remember also from pre-cal that angle had to be in radians for this to work. So we have ways of measuring arcs, right? Okay, so with that knowledge, if we're trying to take an infinitesimally small little polar rectangle, we need to know its area. Then do you agree that it would be approximately the area of that rectangle? Do you see that? Now it's not perfect, right? We have some error in there. But as this gets infinitesimally smaller and smaller and smaller, doesn't this area get small? I mean, this error, E-R-R-O-R, doesn't that error basically go away? Yes? So in the infinitesimal, this error is negligible and in fact goes to 0. So if we can just find a formula for that, we'll be good. So what we use is, for this side of the rectangle, we use this arc length. And then for this side over here, we just use this length. Okay, yes? Now remember, in a polar rectangle, as you swing this way, that's your angle changing, right? As you move out like this, that's your radius changing. We have two variables, r and theta, instead of x and y. So if I want to measure this side right here, this will be how much my radius changes, doesn't it? Isn't it? Yes? So I call that dr. Just like dx was a little infinitesimal change in x. But this piece right here is not d theta. That's what a lot of people think. Well, that's just d theta. No, d theta is a measurement of the angle, isn't it? You actually need the length of this arc. And so you measure from here to here. We call this r, right? If this is d theta, then we're right back to this picture, r, but then this is d theta. So the length of this little arc would be r d theta. Understand that? Yes? Okay, so dA becomes r dr d theta. These three things multiplied together. This times this, yeah? And it doesn't matter what order we do this in. Questions? So here's the summary. If we want a formula for a double integral over a polar region, where our region is defined as all points in two-dimensional space given by r theta. Now be careful, r theta here is not an x and a y, right? It's a distance you walk and it's an angle you turn. It's all the points defined by those two conditions where your theta is between alpha and beta, your r is between a and b. It's Still the double integral that we had last class over r with respect to area, but I'm going to change x over from Cartesian to polar. And we said that the relationship between x and polar is that x is equal to r cosine theta, isn't it? Yeah? And that the y changes from y to r sine theta. Our dA, we just showed in the previous picture, was r d theta dr, right? Didn't matter what order that was in. And then our limits of integration were alpha, beta, and a and b. Do y'all follow that? The important thing, the major important thing, is that if you ever have a problem that's Cartesian and you convert it over to polar, you will always have an r appear in your integrand. The r will always pop up. Later on, we're going to see that comes from a formula, but for now, okay, just remember that for polar, the r is there. That's the biggest mistake I see students make. They go from Cartesian to polar, they do everything correctly, they set up the integral, they forget the r. So we're going to do this example here. Find the volume of this. Find the volume under z equals 3x plus 4y squared on the region bounded by x squared plus y squared equals 1, x squared plus y squared equals 4, with y being greater than or equal to 0. All right, so just like before, what we want to do is draw the region first. Okay, so let's draw our region of integration. My region of integration is bounded by this circle, right? That's a circle, and this circle, and y has to be greater than or equal to 0. So x squared plus y squared is 1, is the unit circle. And then we have x squared plus y squared equals 4, which is a circle with radius 2. And finally, y must be greater than or equal to 0, which means that we're only looking, what, above the x-axis, right? So everything above this x-axis. So do y'all see the region we're talking about? Yeah, bounded by all three. That's it right there. Now let me ask you something. This problem has said nothing about polar coordinates, has it? I could have given you this problem last class. Could you do this problem using what we've done? Like, does that fall into one of the categories of a type 1 region or a type 2 region? So you remember what we did to do this? We just drew a little arrow. And we need to make sure that if we're going to do type 1, the arrow was vertical. And that as we move that arrow left and right, that the top and bottom bounds always stay the same, right? So what if I draw an arrow right here? That top blue one, right, is always going to be on top there. And then the green one is on bottom until I get to the red. And then it switches, doesn't it? Like if I move this arrow over here, the top one's the blue, the bottom one's the red. Now, see how it's switched? And then once I get over here, past this point right here, then it's going to switch again, isn't it? So I could do this as a type 1 double integral from last class, but I'd have to break it up into 3 separate regions to do it. Do you see it? Okay, so I'm not a big fan of that, especially if I realize that this is a polar region. This is a polar rectangle, isn't it? So in terms of this region, give me that in polar. What is the restriction on theta and the restriction on r that would draw that same region? So how about theta? How are you going to draw all the points in here? Yeah, you're only allowed to point between 0, right, to pi. And then as far as the radii are concerned, the minimum you walk out is what? The smallest that you can walk out would be to get to the red, right? So you walk out, what, 1 would be the smallest? And then the most you could walk out would be 2. Does that make sense to you? You're taking all points where you're turning between 0 and pi, and you're walking out between 1 and 2, and it should draw this shaded region in here. Okay, so we've got the region under control, I think. What is the function f of x, y that we are going to integrate? It's this right here, right? Solve for z, but it's already solved for z. So 3x plus 4y squared. I'm trying to do this double integral right now. I've already convinced myself that the region is better suited for polar than it is for Cartesian, so I need to convert this from this to polar. To do that, I have to evaluate the function instead of at x, at where? X is replaced with r cosine theta, and here y is replaced with r sine theta, and then dA is r dr d theta. Now, this does not matter. Right now it doesn't matter because what? This order doesn't matter why? They're both the theta and the r are both restricted between constants. And from the first time we talked about double integrals, if the two limits of integration are constants, the order of integration can be flipped. So I could put r dr d theta, or I could put r d theta dr, but then that would determine which numbers go here. Okay? No questions yet? Okay, let's go ahead now. Let's take the function. Let's replace all x's with r cosine theta. Let's replace all y's with r sine theta. And let's rewrite that right here in the double integral. So it'll be double integral. I'll leave it as r for now. Let x go in there. So it'll be 3 r cosine theta. Agreed? That's 3x plus 4 times r sine theta squared. So how about r squared sine squared theta? Then r dr d theta. I need to put my limits of integration over here. I probably should have done that already, but my order of integration, I'm going r is the inside, theta is the outside, so I should have what on the outside integral? 0 to pi, and then 1 to 2. And that'll be the integral I need to figure out. So integral, double integral, 0 to pi, 1 to 2. I'm going to rewrite this. I'm going to distribute the r through. Is that okay? 3r squared cosine theta plus 4r cubed sine squared theta dr d theta. And that's it. Now we just tackle this. Any questions? I'll go ahead and do this one. I'll finish it out. All right, let's first integrate with respect to r. By the way, you could split this, all right? I don't know if anyone's noticed this, but you could do 2 double integrals because you have addition. And then this double integral right here, since r and theta are separated by multiplication, you could break that into 2 integrals being multiplied. I'm not going to. I just want to point out you could. So here, what is the antiderivative of this thing with respect to r? So r cubed cosine theta plus r to the 4th sine squared theta. That's your antiderivative, right? I'm evaluating that where and where? r equals, right? R equals 1, r equals 2, like that. And then d theta out here. So we're going to plug in 2 first, figure out what happens, subtract what we get when we plug in 1 for r. So we have integral 0 to pi. Let's see, we should have 2 things here. So what happens when I plug in 2 for r? 8 cosine theta plus 16 sine squared. So 8 cosine theta plus 16 sine squared theta. And then when we plug in 1, we get cosine theta plus sine squared theta. And now we can clean that up. So we have equals integral 0 to pi. How many cosine thetas do we have? 7 of them. 7 cosine thetas. And then 15 sine squared theta d theta. And now we're back in Cal 2. So I think the first one's pretty straightforward, right? Antiderivative of this is straightforward. How are you going to handle the antiderivative of sine squared? What's that? U sub? What would your u be? We're not doing that, right? That's done? We don't have to worry about that? No? Power reduction formula. Power reduction formula. Remember this formula? We had 2 of them. It was cosine squared theta equals 1/2 plus 1/2 cosine 2 theta. Then the other one was sine squared theta equals 1/2 minus 1/2 sine 2 theta. Those look familiar to you? Should have used those in Cal 2. So I'm going to use this one right here. Oh, wait, hold on. Oops. Sorry. Cosine. The only difference between the 2 formulas is a plus here and a minus here. All right, so before I do the integration on this one, I'm just going to rewrite the whole integral. And I have 7 cosine theta, and then plus 15 times this, but that is this, right? So distribute a 15 through here and here because it's 2 terms. So I should get 15 halves minus 15 halves cosine 2 theta d theta. Now each one of those should be pretty clean. No questions? Antiderivative of 7 cosine theta is 7 sine theta. The antiderivative of 15 halves theta. Antiderivative of this, what's the antiderivative of cosine 2 theta? 1/2 sine 2 theta, but then hit it with that. So negative 15 over 4 sine 2 theta. Evaluated theta equals 0, theta equals pi. All right, let's plug pi in first. I think good things are going to happen here. Sine of pi is 0. Sine of 2 pi is 0. So that's all going to 0 out, but we'll have 15 halves pi, won't we? So 15 halves pi minus, now let's plug in 0. And I think everything zeroes out here, right? Sine of 0, sine of 0 is still 0. 15 halves times 0 is 0. So that's it, right? 15 pi over 2. Yes.
You remember how last class we did a type 2 region,
Mm-hmm.
and we switched the inside and the outside bounds
The inside and the outside bounds.
on the double integral?
We switch the inside and outside bounds.
Yeah, it should be right.
Uh-huh. I think I know what you're saying.
Switching the order of integration.
Yeah, that. So is that gonna happen ever with polar?
Oh, you mean like, yeah, you mean like we had an integral and then from the double integral we drew the region and then we switched it from type 1 to type 2 and then
because we had like.
we are not going to do that in polar.
So this is always gonna be it.
Well, we are going to do a type 1 region in polar, but we're not going to do a type 2 region. So we won't be able to switch from type 1 to type 2 because there won't be 2 to compare it to. Yeah. Okay? What do y'all think of that? It's kind of neat, huh? Here's what we did, by the way, just so you can see. Here's our integration region in three-dimensional space. Here's the surface that we were integrating. And just that region plugged into the surface gave us this. Whoa. Okay. And then if we bring in the solid that we were talking about, that we tried to find the volume of, it's there, and I'm going to take everything else out. So you can see that this solid that we found the volume of, part of it was above the XY plane, part of it was below. But it looks like there's more above than below, right? So we should get a positive volume, and we did. We got 15 pi over 2. Find the volume bounded by the paraboloid z equals 4 minus x squared minus y squared and the xy plane. So this is a paraboloid. Paraboloids look like bowls, don't they? But this bowl actually opens the other way, and you can tell because you have negative coefficients in front of the x and the y variables. So if I were trying to get an idea of what this looked like three-dimensionally, right, if I'm trying to graph that in 3D, if x and y were both 0, my z would be what? 4? And then what about if y was 0 and x was 2? If y was 0 and x was 2, wouldn't I be 0? So if x is 2, y is 0, I'm here. If x is 0 and y is 2,